So I'm just going to do a quick demo using an object which has a curved surface and shine a laser upon it to demonstrate how this actually works for the people that can't scale. What you see here is a crash cymbal from a drum kit, and you can see it has a curved surface, and this can be considered to represent a portion of a sphere. Now if I match this up as best I can to the protractor to scale, I'm getting about 15 degrees across this section here. And now remember, we're only dealing with 1 degree, and then within that 1 degree you're actually only going to be able to see this light spreading across the water up to the horizon. So if your horizon is 3 miles away because you're standing down at the beach, you're really only seeing 3 miles worth of water, 3 miles worth of light reflecting off that water. As you're standing down at the beach, you're really only seeing 3 miles worth of water, 3 miles worth of light reflecting off that water. As you're standing down at the beach, you're really only seeing 3 miles worth of water, 3 miles worth of light reflecting off that water.
You serious?
So to the scale of this image that I've created using the overlay, you're talking about an area not just only a single degree, which as you can see pretty much looks flat anyway, but probably something like the thickness of this line, which might actually be too much. So you're talking about a very small surface area again. So all we need to be able to do to demonstrate that this is a false claim is shine a light here and see if we can cover that area or more. So here is a video showing that light, as you can clearly see, spread over a much larger surface area. You can even see that the light appears to follow the curve of the surface. It's probably around 8 to 10 degrees at a rough guess, based on the scale established earlier. It's certainly a lot more than a single degree, which would be more than enough to prove the point. You can see I'm using a laser, so the source is a single straight beam of light, no trickery involved, and it's simply due to the angle it's able to spread over several degrees at the surface. So this claim about the necessity of flat water is nonsense. Again, this all comes down to scale. Looking at these other stills I've taken, what I've done is I've reduced the exposure so there's less glow from the light, and then I can zoom in and show you that because there are grooves on a symbol, it's a similar situation to the water with the peaks and the troughs, as I was saying earlier about water. It's not actually a flat surface, so these little grooves represent a similar situation where the light is being broken up, and you can see there very clearly it's covering several degrees across the surface. This would be the equivalent of looking several 100 miles and still being able to see the line of light from the sun coming right up to your feet. So, another flat earth falsity debunked. So now in this next section, what I'm doing is just, I want to explain how the beam is affected by reflecting off of different surfaces. And demonstrating how the main beam itself works. It's a pencil beam, and the fact that the beam itself isn't going to contaminate the results the way a normal torch would. So at the moment I've got it bouncing off of something that's reflecting the light back, which is why we can see the green light on the wall to the left behind the symbol. But
of course the flat earth geniuses have to point out that the water in my demonstration is on a flat surface, not a curved surface, as per the earth. And we see that in many of the comments below my video. So, as always, you know, the flat earthers are frustrating, and there is always something else that they come up with that you have to counter. And so I was going to break out the gym ball that I bought several weeks back to follow up with a further demonstration about reflections even on curved surfaces, when this link was dropped to this video by TJ Waits, and he has done a very good demonstration and saved me all of the trouble because he has done exactly the same thing I was going to do. So let's have a look at his video, which is done very well, and I'll put a link in the description area, and you might like to head over to his channel and subscribe. So here is a gym ball, and he has put a strip of foil on it. So here is a gym ball, and he has put a strip of foil on it. It's wrinkled up to simulate waves. And he's got his LED torchlight at the end of the hallway, and here we go. Let's have a look. Let's go down by the surface, and what do we see? A pillar reflection, or a long reflection on the surface, on a curved surface. Yes, that's right. You can have a long reflection on a curved surface. And he further demonstrates that even without the foil, the ridges on the ball simulate waves, and by rotating the ball, it's evident that more ridges or waves will create the same effect. So yes, it is possible.
Minds will blow.
Okay people, I've got another plane mirror experiment for you. Scaling up this time. We've got a 5 metre plank and I've covered it in aluminium foil tape to create a mirror effect. I've got my LED bike light down at this end. A bit of a diffuser so it doesn't make too much glare. Okay, and it's bending off. As you can see, it's not quite touching the bench. I've got a piece of string for a pulley so I can level it while I'm filming. Right, let's see how we get on. Okay people, bendy mirror, level mirror, bendy mirror, level mirror, bendy water, level water.
Yeah, and see, that's what the problem was.
From the viewer's perspective, this results in a line of brightly lit water, as the most direct light rays from the sun shine down to the water and reflect back up to the viewer's eyes.
Bendy mirror, level mirror.
And reflect back up to the viewer's eyes.
I said, hold up, wait a minute, something ain't right.
Let us learn the 2 laws of reflection. The angle of incidence is always equal to the angle of reflection.
The angle of incidence is always equal to the angle of reflection.
Because then I start to taste them. I say,
If the angle of incidence is 30 degrees, then the angle of reflection will also be 30 degrees.
If the angle of incidence is 30 degrees, then the angle of reflection will also be 30 degrees.
Remember that these angles are always measured from the normal, not from the mirror. The incident ray, the normal at the point of incidence, and
The normal at the point of incidence
the reflected ray all lie in the same plane.
all lie in the same plane.
And reflect back up to the viewer's eyes. Remember, the surface of the Earth only curves 1 degree every 69 miles, so there is no reason to expect that the curvature would have a visible impact on the line of solar reflections visible to the viewer. It is way too subtle to see. The flat Earth argument here really makes no sense.
and then I start to smell them. So it's like the smell like tastes like other. So I I knew something was wrong.
Here's an excellent example of how the sun reflected on water should appear if that water was curving round a ball. This is a screenshot from a video by COFO72. It's called Flat Earth Pieces, and it's part of a compilation of clips showing the moon as seen from New Zealand and the USA at the same time. Very much worth taking your time to check out. I've put a link in the description. So thanks a lot there for this excellent addition, and what I would say is proof that when we look out over the sea at sunset, or even when we see the moon above us, we always see the reflection going in a straight, level line across the water. If it was curved in any way, we would see it curving like we do in this picture, as the sunlight reflection appears to curve up the wave. That's if you just turn this around and imagine it the other way, going off into the distance. That's what we should see if the Earth was curving and the water was sticking to a curved ball. So as a comparison, here is what we usually see when the sun sets over water. It casts a straight, level reflection, no curve there, across the flat water. And at the end of this, you'll see as the sun sets how it kind of appears to veer off to the right. I'll leave that to your own discretion as to what you think is happening there. Thank you very much.
I said, hold up, wait a minute, something ain't right.
Howdy people, I'm going to try a little experiment tonight. Plane mirror physics. Managed to purchase a 1 meter by 60 centimeters of a flexible mirror. And yeah, let's see if we can't get the reflections to match up. So first experiment, we're going to go for the globe model. I have a curved mirror. I'll stop my flexible mirror to a piece of ply, screwed it to the bench, and wedged it down to create a nice even curve. Okay, let's see how we get on. Okay, you go. There we have it. Okay, this time it's a flat level surface. There you have it. Just like how we see moon reflections and sun reflections. Plane mirror physics. Okay, this time I'm going to use a little low powered rather than a high powered LED. See if we can't get a different effect going. Again, bendy water. See how we do. Okay. And again, flat plane. Okay, this is just an add-on to my plane mirror physics experiment that I did the other night. I had a comment back saying that I'm only bending in one direction. If it was a globe, it would bend in both directions. Which is, yeah, fair enough comment, but when we say why is the horizon flat, then they say, well, you know what they say about that. But anyway, another experiment. As you can see, the level isn't setting flat. Are you with me? As you can see, this time we're bending in all directions. Okay, so the same as last time. To double check, because it's a different take. This is the bendy mirror, bending in both directions. Okay. Everyone in a grill. Okay. There you go. Same as last time. I'm going to try again for the little LED marker light, a low powered light. Again, bending, bending. There you go, folks. This one's just a reminder. It's the low marker on a flat plane mirror. There you go.
Smart learning for all.
Topic: convex mirror. Convex mirror forms a highly diminished image, thus making the traffic look much smaller. As a result,
Convex mirror forms a highly diminished image, thus making the traffic look much smaller. As a result,
this is a convex mirror, so it's bulging out in the middle toward us. And I'll be doing the same experiment we did with the convex mirror and with the concave mirror, that is, and I'll be backing away from it and looking at what the image does.
Thus making the traffic look much smaller. As a result,
so I'll start with my nose up against the mirror. It's an upright virtual image, proceeding out to the focal point. Still an upright virtual image. To the radius of curvature, we're still upright and virtual. And then beyond that point.
So think about flat mirror. That's what we're going to start talking about, is our flat mirror now. Okay. So when we look at this, okay, there's a couple things we need to point out. Okay. The distance between the object and the mirror is the same as the viewing distance between the mirror and the image. So in other words, if this distance here is 1 meter, then we will see it as being another meter away, so that it will look like it's actually 2 meters away. Okay, that's what that means. And that's true no matter what this distance is. If it was 2 meters, it would look 2 meters on this side and it'd be 4 meters total. The other thing that always happens with flat mirrors is the image will always be the same size and the same shape as the object. Okay, it's not going to suddenly become smaller or bigger. It will always be the same size and shape.
the image will always be the same size and the same shape as the object.
It's bulging out in the middle toward us,
thus making the traffic look much smaller. As a result,
always happens with flat mirrors is the image will always be the same size and the same shape as the object. Okay, it's not going to suddenly become smaller or bigger. It will always be the same size and shape.
Let's come together right now. Oh yeah, in sweet harmony.
The final one is that one. And I'll tell you how to break out of it.
To show how a ship is brought into a harbor at night, we will start by assuming that at 2010, the Savannah has fixed her position here at latitude 37 degrees 36 minutes north, longitude 74 degrees 47 minutes west. Her course is 230 degrees true, and she is making a speed of 20 knots. As the visibility of lights is computed for clear nights, we will also assume that the visibility is unlimited. Observe that the course as laid down heads directly for this temporary flashing buoy, which has replaced the Chesapeake lightship. Continuing to study the chart, observe that these primary seacoast lights may be sighted. Hog Island Light, 14 miles. Cape Charles Light, 20 miles. Cape Henry Light, 19 miles.
Remember, all I'm offering is the truth, nothing more.
And then we can see an example of this, a perfect example, through Mount Hood, reflected in Mirror Lake in Oregon, United States. And then we can see it in all of these examples as well. And what we notice is that the angle of incidence equals the angle of refraction. Therefore, if the water were not a perfectly flat, mirrored surface, it would not produce the identical image. However, we see, even on vast bodies of water, such as this one, which is taken on an oceanic body in the north of Canada, we see that this can occur at vast distances and that the water has not curved whatsoever. And we also have the example of the moon's light and the sun's light being shown on the water and being seen at any distance proves that the water is not curved, and therefore the earth cannot be curved.
ship gradually disappears until the only thing visible is the tip of the mast.
There's a Gaussian sphere or Gaussian dome boundary layer that allows us to maintain pressure under it, but above that would be the crystalline liquid superluminous fluid triboluminescent liquid type of region. That would be the firmament in basically this cube, just kind of represents it, but I would normally put it as spheres upon spheres upon spheres.
Okay.
Because we do see that when you look at the sky at night, right, you'll see that like the Milky Way has a shadow, right? One side is a mirror of the other side. Like the lit side is mirrored by the shadow side. When you look at stars reflecting in water, some will be duplicated in the sky, and you won't see them in the water. But there's more
wow, yeah. You gotta show that, Chris. Honestly, brother.
I can try and pull up some other pictures here too. This is just an image I grabbed of. You can just go grab some high quality images of the Milky Way, preferably if they're a slightly overexposed one. So this is an image of just the Milky Way, and I was just kind of pointing out that if you can take a grease pencil, whatever, print off a picture of this, and if you can see my little pointer cursor, if you trace down one side of the Milky Way, and you can actually trace the light side, and then you can trace the dark side, and you'll see that it's an exact perfect mirror image of itself, right? So that, to me, indicates that you're looking through double layers. So it's one layer reflecting the top layer, and in between, you're actually looking through it at a bit of an angle, so you're seeing something that's actually through the other side. And when we zoom out a little bit, you'll see that in the water, if you compare the number of stars in the sky compared to those in the water, you'll see that you can line them up quite well with the brighter ones will actually line up and reflect in the water. but all these other ones are missing. Like, they just don't appear in the water at all. And there's lots of images. Just pull up, flat water lake, saltwater lake, star, night skies, and you see it's pretty consistent with all the photography. So to me, that just tells me you can line up these two stars here with these two stars in the water. Sure, there's a bit of an angle because you're an observer on the ground, but it doesn't account for the lack of stars in the water that should be there.
So basically,
and they're just not.
What you're saying then, Chris, is because we're seeing this effect, that these stars, the star field, actually has a somewhat of a polarized direction to them. Is that what I'm hearing here?
Exactly. Like, so the level or the layer of the star field in the celestial dome, they call it the firmament, with the crystal median, superfluid crystals, it polarizes light in such a way that some of the light is coming towards us from the crystals in the star field, stars, right? Some of it's coming in our direction. Some of it's going up, back out towards the top layer of the dome firmament, and you're seeing a secondary image being created. But now what you're doing is you're looking through a one-way mirror, but there's two layers, so you're looking like into an infinity mirror, right? So it's just reflecting itself and reflecting itself and reflecting itself, and you'll see millions of stars when in fact there could only be a couple 100,000 or whatever. But you keep seeing over and over and over the same star doubling, duplicating itself. So it's polarized in a direction. It certainly has a direction to it.
Wow, that certainly goes against the heliocentric model, doesn't it?
Oh yeah, it certainly does.
Yeah, but yet there it is.
And so I see it. I certainly see it as being under pressure, because you need the pressure to create sonoluminescence. You need the pressure to create crystalloluminescence or triboluminescence. So when you apply pressure to a crystal, you get piezoelectricity, and it'll glow. Right?
Yes.
So it certainly has substance. It's under a lot of pressure. Obviously, it's impenetrable, right? And everywhere you look, it's the same type of process.
That is astounding.
I said, hold up, wait a minute, something ain't right.
But
so I knew something was wrong.
But